things, but in the same time, I will consider example of matrices which are not unitarily invariant, and so that there are some very specific features that coming from this point. So in this context, we'll consider a multi-matrix ensemble, a multi-matrix problem, which means that we are in the context of Roland-Speicher lecture about free probability. Moreover, we'll consider Wigner matrices. I will recall what is this model later, but these are non-Gaussian matrices. And non-Gaussian matrices, in this context of covariance of traces, will give some non-universality, as we would say. And the purpose, more specifically, is given, so AN, a family of random or deterministic matrices. We consider a model such that we have the limit in the notion of distribution in the sense of free probability at first and second order. So at first, second order means that phi1 of P, which is the limit of the expectation of 1/n the trace of a polynomial P in the matrix, this is exists for all P, which is a non-commutative polynomial in the matrices and their adjoint. We say that it is a star polynomial. This is the convergence in first order distribution. And we have second order convergence, which is the convergence of the covariance of the trace of P and the trace of Q. As well, this limit exists for all PQ. So this is a situation which is kind of generic, of course, and usually you can say much more things about this model. But what we want to do somehow is as much as possible to explain phi2 in terms of phi1. I will explain how we would like to do that and why it's kind of strange to try to do that in this context, but it's possible. And maybe it sounds kind of obvious if you just think at a single GUE matrices and look at counting planar objects and surfaces. But here we have Wigner and deterministic matrices. So considering this covariance, we have a lot of structures which are carried by this ensemble of matrices. And this is what we are going to describe. So first, I will explain the model, and then I will start stating the results that I developed in collaboration and in another project such as by myself. So let's start to define the model. So I consider independent and deterministic matrices. So the family AN will be the union of two families that I call Xn and Yn. I usually use this kind of strange bold character to mean that this represents a family of objects. And here, for the Xn, I consider a family of independent Wigner matrices that I do not assume to be Gaussian in general. And for Yn, I consider a family of deterministic matrices. So let me recall what is the Wigner matrix if you don't know this. Recall that Xn is a Wigner matrix whenever it is an Hermitian matrix, so that if I denote its entries normalized by square root of n like this, by xij, this xij they are independent up to the Hermitian symmetry. And the non-diagonal and diagonal entries have some specific distribution. Let's say mu outside of the diagonal, which is a complex distribution on the complex plane. And here distribution mu, which is on the real line because it's the So this Camille, is what we call, yes?
Okay, yeah, you can continue. Sorry, there was a problem with the connection, but you can continue.
Is it okay? Tell me.
Yes, it's okay now.
Very good. So this is what we call a Wigner matrix today. And in the first step, I will consider this ensemble with a technical assumption. Not technical, but we need this assumption. Yeah, it is technical. We assume that when you take a random variable outside of the diagonal, it has the same distribution as this complex adjunct. And this turns out to be useful to use our tools, but it's not really a priori essential for what I would say. But it makes this matrix permutation invariant, which will be useful for us. And so this is what we have for the Wigner matrices. And this is only what we want to assume. But we want to assume the degree of freedom that this distribution mu and nu can be arbitrary. And when mu and nu are not a Gaussian with good specific variance, this matrix is not unitarily invariant. Moreover, about the deterministic matrices, I assume that they are uniformly bounded in operator norm. So this is a kind of classic setting in free probability theory. And the first order distribution of this model is well known. What we want to investigate is the second order distribution. So let me state two theorems. An old one, which goes back to the beginning of the theory by Voiculescu, Dykema in this non-Gaussian case, which tells us that the first order distribution, phi1, exists and depends only on few parameters, which are the variant of the normalized Wigner matrices for each Wigner matrix. Remind that we introduce a guy which is normalized by square root of n in the definition. And then the limit of this guy will depend only on this when we are talking about the Wigner matrices, only on the variant. So that if I divide each Wigner matrix by the square root of this quantity, I have normalized everything, and there is universality. It does not depend on the other details which define a Wigner matrices about higher moments or different moments of the measure mu and nu that I define. And it depends also from the point of view of the deterministic matrices to the limit of 1 over n the trace of a polynomial in Yn for all p. This is the limiting first order distribution of the deterministic matrix. And it is now some results because a priori, this is not obvious that other statistics on Y disappear in the large n limit. Okay, so this is something which is known since quite a long time. And what we investigated more recently with co-authors, namely James Mingo, Sandrine Péché, and Latent Speicher, is what is the limit of the second order distribution for this model with this degree of freedom. And we computed a formula for the second order distribution given two monomials, and we get a huge formula, which depends on much more parameters. From the point of view of the Wigner matrices, it depends. Assume that the variance is fixed and it's one for each matrix. Moreover, it depends on the first moment of the normalized entry. They depend not only on the variance, but also on what is called the pseudo variance. Well, I don't put the modulus here, and we make a difference for complex random variables. And it depends also on the diagonal variance of the entry. If you play on this degree and freedom, you will get different global fluctuations of this kind. So this is something which is known from classical random matrix theory when you take a single Wigner matrix. But what our result gives, which is really new, is the dependence on the deterministic matrices. We observe that this quantity is not sufficient to see what will be phi2. And what we need is much more complicated quantities, namely the limit of the trace of an entry-wise product. This is this symbol for the entry-wise product of a polynomial in Y and another polynomial in Y. Also, it will depend on 1 over n the trace of a polynomial in Y times the transpose of another polynomial in Y. These two limits are ingredients that you must know if you want to describe the covariance of traces of polynomials in these two ensembles of matrices. So there is a formula which tells you everything about all this work. And this formula is actually huge. Just 1 hour ago, you have seen a formula by Speicher, which describes what happened in the case of unitarily invariant ensembles, like the GUE. And this new formula is 5 times more complicated because there are 5 terms that correspond to modification of the GUE. So that's fine to be able to see such an example. I would just like to mention that this phenomenon, and specifically this kind of parameter, was observed to appear in another model studied by Vasquez-Becerra in the context of liberating sequence of matrices. So just to mention that what happened in this model is maybe something that you can meet in a much more different situation. This is what happened here. And so what, in the second part of this talk, now that I have stated this, I would like to find something simpler to describe phi2 than a huge formula involving all of them. For this task, I will consider some assumptions. So I will first assume for the Wigner matrices that the pseudo variance here is 0, the expectation of the NC square. And I will do that to simplify the problem because from this assumption, I know that this term will not appear. And it is quite simple. So this is just something to make life easier. I will also assume an assumption which is very different. I assume that the limit of the normalized trace of an Hadamard product is the same as the limit of the product of normalized trace of P of Y times Q of Y. And this is not something like a technical assumption. This is very something which is a uncommon property. Uncommon property. For instance, if you take diagonal matrices, they will not respect this rule. I'm talking about some kind of deterministic matrices which are very specific. And there is a purpose for that. And I'm going to explain this. Why considering such specific topic? This is because when the Xn are GUE matrices, we have the notion of second order freeness. It's been described by Roland just before. And you get a formula to describe this, but there is a formulation of second order freeness that I like, which tells you that the fluctuation pi2 can be explained in terms of the first order distribution by a collinearity property. Times Q. And for all P in some space, that has to be defined. So this presentation was not written like this before, but this is an equivalent notion of the second part of the definition of second order freeness using the first order freeness. And it's more like you have a bilinear form here, and you want to describe it in terms of your canonical bilinear form that you assume to be the first order distribution. And you associate the bilinear form like this, and you look for space of functions such that a nice formula like this holds. So this is the spectral reduction of bilinear maps, actually. Okay, so this is what happened actually with GUE. And what we want to do is to adapt such a simple formulation for this context that I try to convince you it's much more complicated in its details. And it turns out that this is kind of possible. Let me explain this. We prove that we can adapt this notion. So there will be an adapted notion of collinearity relation, which holds for this Wigner matrices. And this is kind of surprising because the Wigner matrices, the fluctuation here does depend on a lot of parameters, whereas in the right-hand side, I have something which depends only on the variance of the Wigner matrices. So that such a relation cannot explain entirely what is the fluctuation of my non-universal model. And so this adapted collinearities that I will to introduce by defining good space EM will come together with another relation. And that invites us to see the fluctuation as a derivative in a good space. And it will be a kind of Leibniz relation. And so at the end, for this model, which is more general, we will have the continuation of what we know about unitarily invariant matrices and some very canonical formula. Okay, so this is the purpose of the continuation of the talk. If you have some questions, if something is not clear at all, you can interrupt me. So now we explicit the space En in case of second order freeness. We then explicit what is this En adapted for Wigner matrices. And then I will, doing this, I will add more structure and I will be able to introduce in a natural way the Leibniz property. So let me remind you that if you have a family of non-commutative random variables, this object is made to be seen as the limit of a family of random matrices. And the non-commutative distribution, phi1 of this family is the map which associates to any polynomial the trace of this polynomial in matrices. And this is a trace, phi1, and which is the limit of 1 over n, the trace of P in AN. We take an expectation if you want, and the matrices are random, right? And you know that when A is, let's say, the union of some families, I'm taking some disjoint union, but as we discussed this morning, you can allow the units to belong to several families, but I will write things like this. The AL are free if and if we have a vanishing relation. In some space, En, for n greater than or equal to 2, where En is a space of all products P1, Pn, such that Pj is a polynomial in one of the families. It is centered at first order. And these indices are alternating. L1, Ln. So this is a definition that we have seen this morning. And how to describe second order freeness now? They are second order free, if and if they are free, plus an additional condition. And I will not repeat the condition of this morning, but give another one, which is just a makeup of the other one. And this is on the form of the collinearity relation that I wrote before. P star Q is delta NM n phi 1 of P star times Q. And this holds for all P. It would be miraculous to have something this in En, but it is actually in another space, and I will explain why. So these spaces are just a little modification of this one. First, we assume that the indices are alternatingly, are cyclically alternating, as we have seen this morning. But moreover, I use the fact that the trace of AB is the trace of BA. I think about this property, okay? And I can use this property to each argument of this function because it's the covariance of the trace of this guy, the trace of this guy. And this specific symmetry is not true at the level of this linear form. The trace of ABC is not the trace of BAC. This is why such a relation can be true if we use this symmetry in the input and symmetrize this product. 1 over n, the sum over A from 1 to n of the first plus I, the P I1 plus I, up to the Pn plus I, with a cyclic notation from this. So here it is. This is the same relation as this morning, and this is just a makeup about using this sum and injecting it there. But this is a notion of second order freeness by Mingo and Speicher. Okay. So what we want to do now is to adapt this in the non-universal context. And what we will consider is now random variable in what is called an operator valued probability space. Namely, we are considering more structure on the variable, which reflects more structure on the matrices, that will be useful to explain the distribution phi 2. And if you have more operation, we have more opportunity to write equation between this operation. And this is what we do now. What we do is that we augment the space of non-commutative random variables with an operator delta, which is called a conditional expectation. So this is a context defined by Voiculescu 40 years ago. Delta, which is think as the limit of the diagonal operator which take a matrix and gives a diagonal matrix of its diagonal entries. Okay, so in an abstract context, you just consider a symbol, and you want this symbol to have the same property of the operation that take a matrix and give it diagonal. In particular, it is a conditional expectation. In this sense, if I take two diagonal matrices D1 and D2 on an arbitrary matrix, and I take the diagonal of this guy, this product, it equals the first diagonal matrix, the diagonal of A times the diagonal of the second diagonal matrix. And if you think about the notion of conditional expectation, you know, in classical probability, well, this is the same, but it is beside it because of non-commutative. So this subject is actually amazing in this context. What we do is we extend the notion of distribution. We denote phi tilde 1 is the map which gives the expectation of the normalized trace in RN. So we take the trace. But here, P, we do not only consider star polynomials, which are products of elements of A, but every expression which involves products and the operator delta. So this is the extension of the phi 1 before, because here, for P, which is called a delta polynomial, or delta star polynomial. An example of delta star polynomial is delta A1, A2, delta A3, delta A4, delta A5, A6, something like this. Put some stars if you want. This is a delta polynomial. And you can sum delta polynomials, multiply by scalar, and you can apply delta and use the conditional expectation properties, and you have a nice algebraic structure. You have a nice algebraic structure of operations, and then you can evaluate the expectation of the normalized trace of this and look at the limit of this guy. You can also look at the covariance, and this is what we consider. We define phi 2 as the family of variables. It is the data of the fluctuation function in A, in P and Q, but no P and Q are delta star polynomials. Okay, so we get more information about the matrices when phi 2 is the limit of covariance of traces, right? And this is in this context that we can write a collinearity property. The adapted notion of space Sn, that I call here Sn tilde, will be, so there is a symmetrization as before on the product, 1 plus A, n plus A, such that each PA is now a delta star polynomial and not just a polynomial in one family. put the J here. Actually, it's ground variables in family. And we assume that this polynomial is centered, but not by the trace, but by delta. Delta of Pj is 0. If you think about the matrix, you're saying that the diagonal of the matrix is 0, not only its trace. It's much more powerful. And the indices are cyclically alternating. Okay, so this is this sum of products is a delta polynomial with a very specific structure. And because of this structure, we have a collinearity property. Then, phi2 of P star Q is delta NM and phi1 of P star Q for all P in this new adapted space F tilde and Q in another space. Okay, and we just change slightly the setting and we get the same result. And this setting, if you discover the operator value notion today, it looks strange, but actually this is something which is very common in the theory. This is just the canonical space associated to the modified notion of freeness over the diagonal. So freeness over the diagonal is a fact that is true for Wigner matrices, but we don't really care because they are free in the usual way, and this contains much more information. But from the point of view of second order distribution, for Wigner matrices, freeness and second order freeness are not so useful, but this second order notion of operator value freeness works quite well to describe this. And this is not everything. If you know this relation, you don't know what is phi2 for a generic polynomial, because you selected something which is kind of restrictive. And of course, you cannot do that because if phi2 depends on a lot of details on the matrices, phi1 depends only on few details. So it is imbalanced if you have only this. And this is why things come with more rules. There is this rule at first order under the assumption that we consider, and specifically the uncommon assumption on deterministic matrices, the phi1 of the diagonal of a polynomial P1 times the diagonal of a polynomial P2 is phi1 of P1, phi1 of P2. So the delta at first order is actually very trivial. And this is the meaning of the uncommon property that I state for deterministic matrix. If it's true for deterministic matrix, it's true for Wigner and deterministic matrix. And so at second level, the second order distribution, the information we need to accompany this rule to actually determine phi2 is the Leibniz relation in this form. So phi2 is the fluctuation of the trace of two polynomials. Assume that two delta polynomials. Assume that the first delta polynomial is of the form delta p1 times delta p2, and the second one is generic. Then we have a Leibniz formula in the following sense. This is equal to the phi1 of p1 and the phi2 of p2q plus the phi1 of p2 times the phi2 of p1q. And now we have three relations: the collinearity relation, the Leibniz relation, and a factorization relation. And what I claim is that giving these three rules, you can finally determine what is the first and second order distribution of a set of Wigner and deterministic matrices by combining the information and just using the first and second order distribution of each matrix. So this works as freeness in more complicated way because we have different ingredients, and we go to the setting of delta polynomials. But at the end, we can decompose, use a lot of times these properties to only pick information from marginal models. Okay, so maybe it's a lot of information. I still have a few minutes, I think. So I would like to talk a little bit about the method of proofs. So the method is based on the theory of traffic. And traffic is the application of the moment method in a certain manner with some knowledge about some functions that are involved in this method. And so I'm going to describe this. If you compute the trace, let's say, of the power of a matrix, and let's say consider the expectation of this trace, maybe you normalize or normalize in a different way. You often write this in terms of the entries of the matrix. So you consider a multi-index, and you take the expectation of the product of random variables. You have A1, A2, AN, A1. Okay? So the partitionist method, partitionist because at the end you write partitions, like non-crossing partitions, often work when you start using here the weak formula. For instance, if you have Gaussian random variable, or you use the cumulant representation of this expectation, the cumulant expansion of this expectation. The trafficalist method works differently. In the traffic method, you momentarily forget about the expectation and find a way to write a trace in some natural way on writing a cumulant expression of the trace, but on something which is more intrinsic to this linear algebra problem. What you do is that you decompose this sum and organizing the terms such that the indices that are associated to different index are equal or different. What you consider is first a partition of all the indices 1 to n, and then a sum over all the indices such that the kernel of this multi-index equals this partition phi. Let me say, what is this kernel of I? It means that P and Q belongs to a same block of this guy, if only if the indices associated are equal. Okay? So we organize things like this. And if you're comfortable with the fact that when we have a trace of a power, we represent a cycle like this, whose number of age is the power here, you will be comfortable with the fact that this guy is a functional on a graph that we obtain from this one. Let's say that this graph is called T. I will denote T pi, the graph obtained by identifying vertices of T in the same block of the partition part. Okay, and let me give you an example. If you look at the trace of AB, the product, it is the sum over different indices of the first matrix entry AJ, second matrix BJA, plus the sum over a single index of the diagonal entry. And we have two terms because we have two partitions for these two elements here. And here, this term is represented by this diagram because I have two different indices there and two matrices. And here, this term is represented by this diagram because this is what we see in this expression. Okay, and so we introduce a language where we have a systematic approach of this, and we can write the trace of a polynomial as a sum over partition of what we call the injective trace of the quotient graph. And so this is a definition of when you write it explicitly, this is like this. And the advantage of this is that in the context of traffic, we have moments in the sense of traffics, which are kind of general. We have a notion of cumulants, which has been discovered by Frank Gabriel. But we have also this notion of injective trace. And Gabriel proved that this is something which is a tool really between the cumulant and the moment, but which is different from both of guys. And it has its own very good properties. And it's a kind of a wavelet in this algebraic setting because it's very sparse representative and so on. And so the goal is to work with this injective trace, and actually it works quite well. If you look at the covariance of the trace of a polynomial in these Wigner and deterministic matrices, so AN is the union of the X and the Y, you can prove that for large but finite matrices, we have a sum in this injective trace expansion, which involves some sum of partition of vertices, and which represents, for each polynomial, you represent a cycle. And choosing a partition like this is identifying vertices that belong to the same block. So it gives you something more complicated and trigated, and you associate a value of it. But in this case of large Wigner and deterministic matrices, if you start from a polynomial, you will get two terms, a good one and a bad one. The good one represents the fact that when you have two faces, you're creating a sphere. Okay, that's very simple. And you're creating the sphere in the good way, as you can imagine. The second term represents the fact that you're first getting two spheres and then just identify them by an edge like this. Okay, so this is two ways where starting from two faces, you get a guy of topology 0. Okay, and this guy is a kind of degenerated version of this one. Right? So the idea which comes from the techniques of traffic that were developed a few years ago is not to take an arbitrary monomial here, but to take something more clever. And in particular, taking this P in the space En, which is this alternative product of delta center-head elements, when you remove delta, you put something which looks more complicated, but actually it's much simpler. Taking the good polynomial, which has alternative product of delta center-head elements, turns out that in this sum, So we have a small term. This bad contribution disappears. Not magically, it's because of the computation, because of property of freeness. Because if you want to do two spheres, you have to make one sphere, but one sphere is the vanishing first order free condition in the context of delta freeness. And so at the end, using this very specific delta polynomials, you're able to only get these pictures. On these pictures, it comes with some weird weight. It's not just counting surfaces, but just counting a quantity using surfaces, but associating to some weights on the deterministic and Wigner matrices. But it turns out that in this situation, the weights are universal, depends only on the variance. And you can cut a sphere in such a way that you recover from the covariance the phi 1, which is the limit at first order. So there is a lot of techniques about this, but I hope this will give you some ingredients, some feeling about how it works. So I don't know if I have more time because it's supposed to be 10 minutes before the. So if
we have maybe 5 minutes.
5 minutes, very good. So I will just give you a last comment if you're still conscious after what you put in your nose. I'm sorry about this. So remark is to go back to the random matrix property. Let's take a polynomial P in this kind of weird space with nice property, and denote Mn the random matrix P of An. In the context of we are considering the centroid trace of polynomials are often Gaussian variables. And this is what I assume now. And having a second order distribution means that we can compute the variance of this Gaussian distribution. So that if we consider the trace of a polynomial, we can approximate it by its expectation, which has to be estimated in some way, and this is a topic of infinitesimal freeness to talk about it, plus a Gaussian random variable. A Gaussian, this is a complex Gaussian. It is centered because the centering is right there. And we know the variance. It is given by the second order distribution. But now we have a guy which is in this space. So the second order distribution can be written in terms of the first order distribution. If it n, little n over big N, the trace of Mn star Mn. So this is a conclusion that we can get from the collinearity property. And this is kind of strange. First, because An is a family of Wigner and deterministic matrices. For the Wigner matrices, we don't know what is the first moment of the entry. The first moment in the entries, in general, is involved in this covariance. But because we took these very specific polynomials, this contribution just don't show up. There is some simplification that made that this is not appearing here. And this space is not specifically made to hide this contribution. It's something which is central for the notion of freeness over the diagonal. Moreover, what says this expression, this approximation, in the left-hand side, what we are looking for is the statistical fluctuation of a trace. Of a trace, we look at a quantity and we look at what is approximately the distribution of this guy on this equation with this covariance. And here, what is the answer is that the order of fluctuation of this guy, the size of the confidence interval, can be compared with this quantity But what is this quantity? If you have a random variable which is centered and considers the trace of A star A, this is the quantum fluctuation. Which means this is the variance, but in the context of free probability. If you consider a state and consider phi of A star A for a centered element, this is a non-commutative variance. And so we prove that the statistical fluctuation of a trace can be written, and they are proportional actually to the quantum fluctuation of this element in the limit when the size goes to infinity. So this is not something I noticed before. I don't know if someone has already made something like this, and I would be interested to know that. So I hope that you did enjoy the talk, and I hope that it will continue and be very nice for you in Munich. Thank you very much.
So are there any questions? So maybe I have a question. So it was not clear to me, how can you get, so if you had matrices which have diagonal 0, but then you said you have other relations to have products. How can you get, for example, if I have the matrix with diagonals 1, 1, 1, 1 and say 2, 2, 2, 2, how can you get the answer for these matrices? Because assuming that the diagonal is 0 is really a lot. Eh? So you need to center in some way, but how can you center?
But are you talking about the Wigner matrices?
Yeah, what I'm saying is in your algebra, so you have a very nice formula when the diagonal was 0. So your expectation is to
You mean inside the definition of this segment space?
No,
what
I mean is you have a very nice precise formula when the diagonal was 0. You assume that if delta of P was 0, then you have some formula, and then you had other relations which you said that with this you can get actually delta in phi on all, phi 2 on all polynomials. What I mean, so you can do for all deterministic matrices or only for the ones which have a diagonal which is 0?
But I don't know where you put this diagonal 0 assumption in the game, because what I talk is about product of guys like this, such that the delta of each guy is 0, but not the delta of all these guys. I will consider this trace. It's trace later, so I don't want this diagonal to be 0.
Okay. So you can write any matrix as a product of this kind of things in some way. This is the point.
Yeah, there is this exercise, and this is really not explicit in this talk, because we have 3 rules, which is a bit unrelated. And at the end, you take an arbitrary polynomial, and you want to prove that in some sense it is the sum of guys of this form or some guys that you don't care about because of the Leibniz formula. And there is a lot of things to be said about this. Maybe you are thinking about delta equals 0 because first order freeness over the diagonal indeed tells you that this guy is 0. Maybe this is...
yeah, exactly.
Exactly. But this is true at first order. When you say that, classically, you just mean something which is too strong to consider a second order property. Because the fluctuation of this guy on its diagonal actually is not obvious, not 0. So what you should better say is that the phi 1 of, let's say, this guy squared, modulus squared, is 0. And then if you replace your delta equals 0 by something like this, you have a property which is more relevant for your context. Because delta of P is not 0, but its a first order distribution is 0. Can you understand the difference?
Yeah. So maybe another very simple question. So the conditional expectation is to a commutative algebra?
In this context.
Yeah, the limit is also commutative, huh?
In
The
this
abstract
context,
limit.
you can assume this because it's true for all n, for all matrices. If I'm right, the way I've written this delta freeness relation, you should write it without this assumption. But I don't know a non-commutative example that realize this property.
Okay.
But you can imagine matrices with non-commutative entries. Look at what are the fluctuation of traces of this guy when you have 3 entries. And I will beg that some non-commutative delta algebra is useful.
Okay, maybe it's time. I will ask you more questions later, but thank you very much for your talk.
Thank you very much.